So as it stands now, we have a working linked list as far as adding goes. Um, so, and just to review, our adding had three scenarios, right? We have three scenarios. The first is that we want to add an item to an index, and that index is out of bounds. The second scenario is, what if that index is adding something to our adding a new first thing in the list? Well, that requires us to just create a node that holds the item we want to add, and attach that item to the current head of the list, and then make the head the new item we just added. Okay? So, and this requires a special instruction on our part, because since the head of the list changed, we had to update the list to reflect that. And once we add in a tail node, you're going to see that we'll have to update the tail to reflect that we'll have to add code to reflect that for tail as well. All right. So now scenario 3 is everything else. And in that case, we get the node before the index we want to insert. We attach temp.next to the node currently at the index. Sorry, we attach the item we're inserting to we create a node to hold the item we're inserting, and we attach that temporary node to the node at the index we want to insert into. And then we attach the node before that index to our temporary node, right? So go back through those videos if you want to recall those, but those are the three steps we want to use. And it turns out that for the remove method, public void, we're actually going to return the item that we're removing. So public remove int index. For this one, we actually follow a symmetrical number of steps. Scenario 1, the index is out of bounds. Scenario 2, we are removing the head. And scenario 3, removing something else from the list. All right, so we'll go through scenario 1 very quickly, right? Out of bounds, right? That's scenario 1. So how do we know if it's out of bounds? Well, if the index we're adding to is less than 0, or we're removing an index that doesn't really exist yet. So if the index is greater than or equal to our size, the size of the list, right? We can't remove index size because that doesn't exist. We can't remove the nth item we can't remove the item at index n in a size n list. The furthest back we can go is index n minus 1. So what we'll do is that we'll throw new index out of bounds exception. Can't remove that. Right? Just something simple and silly. All right. The next thing we'll do is, so that's our case 1, it's out of bounds. Case 2 in add was adding a new head to the list. So case 2 over here in remove is removing the head of the list. So how do I know if I'm removing the head? Well, I know I'm removing the head if I'm removing the item at index 1, so index equals 0. So if index is 0, then I'm removing the head of the list. All right. And then I'll finish listing our scenarios before I start drawing. Okay. So the other case is that I am removing everything else, or anything else, not everything else. So else, the other case is okay. So now, and we do need to take care of this whole returning E. So we're going to basically say, put over here an E to return is null right now, and then I'll return the to return over here, right? All right. So what does removing the head of the list look like? So let's go ahead and draw that, right? So let's go ahead and make a node here. And here we won't have a temp node because, right, we only needed to make a temp node when we were actually making something. So head, another node, and right, I'm just labeling this guy head. But the way it more accurately works is that I have some variable here, right? I have some variable here that says, whoops, head, and it points to here, right? Saying that this one is the head, right? That head is storing the memory location of this node, and the dot next is the dot next to this node is storing the memory location of this guy, and this one is storing the memory location of this guy, and this one is storing the memory location of this guy. It turns out, though, how do I removing this guy is actually fairly trivial, because all I have to do, because let's think about what I want to get done. If I'm removing an item from the list, right? I have to. Where do I want to end up? Regardless of the order of the stuff I want to do. I want to end up in a situation that looks like this, right? If I'm removing the head of the list, what I want to do is end up in a situation that looks like this, with this guy as the head, right? This is now the head of the list. So how do I end up there? Well, it turns out all I really have to do is go and make head point from here to over here. Whoops. Come on. There we go. Head from here, from the first node to the guy after head, because what happens, well, when there's nothing, when this has no variable referencing this anymore, when there's nothing pointing to it anymore, when its memory location isn't stored anywhere, it gets marked by the garbage collector for deletion. And that's exactly what will happen. In other languages, where we manually have to manage the garbage, we'd have to take care of something. But in this programming language, but in Java automatically manages that for us. So all we have to do is just simply move this the .next pointer for head, or sorry, not the .next, but the pointer for head to store here. So head gets stored from here to here. Okay, so that's a fairly straightforward turn over here. And before I go any further, I'm going to remind myself that actually if I'm removing a node, I want to remember to remove to decrement the size. Okay, so if I'm removing the head, that means the index is equal to 0. Okay, and then I need to, there's one more step in here, though, that I just can't label there. The first thing I want to do is get the item from head to, get it out, so I can return it. So I'll just simply say to return is equal to, let's see, head dot item. And it's very important, by the way, to understand that, especially for the exam, and this is a constant thing I see on the exam, that when we're dealing with nodes are different than items. I see people one common mistake I see on the exam is that when people write something that's like an add method, they'll go item.next and completely forgetting to put the variable in there. They'll also try to manipulate a list, given a linked list, but not the node class, because the node class is private. They try to iterate using a while loop while not being inside the linked list. Right? In here you have reference to the .nexts. But outside this program, you don't have references to the .next, right? You don't have references to the nodes. So it's important to keep that in mind. We'll go over that when we go over the practice exam. But anyway, so the first thing we need to do was we store the item, right? And then the other thing we need to do is take this pointer move it from here to here. So, or rather, take the memory location, right? Instead of storing this guy in head, we're going to store this guy in head. So what is this guy from our perspective? Well, this is head, This is the node after head. So this guy is head.next. So all we do is head is equal to head.next. And that's all we need to do to remove that guy. So we'll go over the next. Let's go ahead and test that out. So this is what we currently have. Run, run, run. Okay, so we have DACB. Sorry, we have DAEBC. So I'm going to print out the effect of dot remove, right? Index 0. So we're going to remove index 0 because that's the only thing we know how to remove right now. And then I'm going to print out the whole list to show that basically that we still have the rest of the list, which is kind of important, right? We want to make sure that when this goes on, we don't want to lose the entirety of the list, right? And we'll do this twice. Right, so we removed index 0, we got the item back out, and then we removed index 0 and we got the item back out. So the list does change according to our according to the changes we do make. So that's great. That's fantastic. Okay. So the next thing I am going, so let's go ahead and go to the next video.